Sorry. So, you need to make a computations. In many cases, this psi1 and psi2, at least in the initial moment, are the same, are very close. Since mass of neutrino mass difference is very small in comparison with energy release, so in the first approximation, at t0, at production point, these wave functions are very close to each other. So now let me consider what is this, how they look like. One can find that this psi I xt in many cases can be factorized in the following way. Fi xt multiplied by minus I fi xt. So it can be presented as the product of two factors. One is shape factor, and another is phase factor. Now let me discuss a little bit what is this. So shape factor is usually normalized in such a way that the integral from plus infinity to minus infinity moduli square fi xt square over dx is 1. Okay? So I'm discussing phase factor. So in most of the cases, as we will see, oscillations effect do not depend really on the shape of this factor. And only in very exceptional cases, you really need to know explicit form of the shape factors. One can show that the shape factor depends on x and t in specific form, x minus group velocity time. So it depends on x and t, not arbitrarily, but in this combination. Well, there is a simple derivation of this, but I don't want really to spend much time, just to have feeling what's going on. This means that shape factor describes some structure which is moving with group velocity. Well, I describe the shape of your wave packet. Well, actually, this depends on, for instance, energy distribution or momentum distribution in your wave packet. So when we are talking about wave packet, we mean that we have the system of plane waves with different momenta. So if these momenta have not too big spread, we can proceed with this description. In configuration space, it corresponds to the following form of psi. So it moves in space. And what you see here is that with time, x changes according to this group velocity. So this factor describes motion of wave packet. So group velocity is dE over dP, which is actually equals for free moving particle P over the energy. So the overall picture then is the following. We have shape factor and we have this phase factor, which means that this phase factor is inscribed into the shape factor. Clear? So we have this wave pattern which is inscribed into shape factor. Actually, I will use only half of the plane because in reality you have, of course, actually it's even three-dimensional, even a complex space because these are complex. But for simplicity, I will, and to avoid messy pictures, I will use this type of the description. So group velocity is the velocity with which, say, maximum is moving. So that's moving with group velocity. Here we also introduce phase velocity, which is velocity of motion of the phase. For instance, we can take this phase and to see how it is moving. Group velocity doesn't coincide with phase velocity. So it's kind of funny structure. This moves as a whole, and inside this shape factor, this oscillatory picture moves. So this is more or less complete picture. So now let's come back to our mixing neutrino state. Since we have two mass states in our example, we need to use two wave packets for nu1 and nu2. And therefore our electron neutrino, for instance, is this complex object with two wave packets. So its propagation is described by two wave packets. That corresponds to nu1. This corresponds to nu2. They have different height, so that is proportional to sine. This is proportional to cosine. And we have this type of oscillatory pattern. So I have written just one oscillation phase right here. And in fact, in that expression, I need to use so-called effective phase in my expression with product of shape factor and phase factor. And this effective phase is given by the average energy and average momenta in a given wave packet. So of course in the wave packet you have all the kind of range of momenta and energies, and what is staying in the phase, and I will develop this more, is the average phase, which is given by average energy and momenta. So we can introduce also sigma x, the size of the wave packet. And this is, so to say, picture at the production of electron neutrino. Now what happens further? What happens further? These packets start to move, right? So neutrinos are produced and these packets are moved. Since M1 is not equal to M2, different things happen. One is the phase velocity of this oscillatory pattern is different. Is different. And so, for instance, if in initial moment they were in phase, so maximum here and maximum here coincide, due to different group phase velocities, they will start to move apart from each other. So it will be phase difference developed in this case. So phase difference, which will be the function of time and x. Right? And it is this phase velocity change, or difference of phase velocity change, which leads to oscillations, as we will see. So that produces oscillation. So phase difference change And we call sometimes this phase difference as just oscillation phase. So it's phase difference between this oscillatory pattern and this oscillatory pattern. And it is this change of phase difference which leads to oscillations. The second effect is, since they have different group velocities, these wave packets start to separate. So this is one effect, oscillations. And then we have different group velocities. And that leads to separation of the wave packets. Which corresponds to nu1 and nu2. So if you had an initial moment, the situation when these two were overlapping, so again, of course, in reality, this should be overlapped with that, right? So they are existing in the same space-time point, and just to visualize, to see. But if they are in the same kind of x range, then they overlap, and then they interfere. So, suppose this was an initial moment, but then after some time, you will have the situation when, for instance, this wave packet shifts with respect to the second one, because it has bigger group velocity. So that was initial, that is after some time, but then they completely separate. And of course it will be no overlap, and therefore it will be no coherence between these two, and there is no interference in it. And neutrino oscillations is the effect of interference between two wave packets, as you will see. There's a third effect, actually. It's the spread of the wave packets. This is common in quantum mechanics. Probably you met this already. Because of mass, it's not only they will shift with respect to each other, but they also will become wider and eventually become classical. But I will neglect this effect in my consideration. And mostly will neglect this effect. Although, for instance, for solar neutrinos, this is crucial, so the wave packets just separate and there is no oscillations. So what arrives from the sun to the earth are wave packets of mass states. For laboratory experiments at the earth, mostly you can neglect this, and the main effect is the oscillation effect. No questions?
Can you repeat again why did we have to use effective phase?
Why I have what?
Why did we have to use the effective phase?
The effective, not mass, effective momentum, effective phase. Okay. Yeah. Well, in principle, I have many momenta and many energies of plane waves within the wave packet, right? So wave packet can be constructed as superposition of plane waves with different momenta and energies. Okay? Now, if this range of energy and momenta is not big, then we can introduce average energy and average momentum. I don't want to deal with many energies and momenta. And in fact, I can do this, and that simplifies our analysis. And so I introduce this average energy and average momenta in my wave packets, and that produce what I call effective phase. I will just write this explicitly, and then you can ask, by the way, why not to switch on video? I want to see you. So you're asking questions, and it's like, to replying to empty space, we still want to have not just vacuum around us. Okay, so precisely, let us consider phase factor in more details, and I will explain then what what's going on. So we have the phase factor. Let me put here phase factor. Which is minus I f I x t, which is nothing but I, and here I write average velocity in the wave packet, t, minus average momentum in the wave packet x. So this is important actually. Okay? And then I call these as effective phase. Right? So when I use average momenta and energies in my wave packet, or effective if you want. So Fi equals It minus P NHX. Again, this can be done, and one can show this that works if you have not a big spread of wave packets in momentum space. Of course, if you have huge spectrum, then that may not have any sense. However, if you have small delta E or delta P, which are sizes of the wave packet, if this sigma P are not big, then if they are much smaller than momentum or energy, then you can introduce this average momenta and energies. And for simplicity, I'm using this situation, which actually is realized in real experiments. Okay? Now let us discuss phase difference, which is the key for oscillations. Again, let me repeat that it is phase difference between wave packets, which correspond to nu1 and nu2, that produces oscillations. So phase difference. Delta F is introduced as F2 minus F1. And these are effective phases of two wave packets, which correspond to nu1 and nu2. In literature, very often people are using the following assumption that the average energy of E1 equals the average energy of E2, and that equals some E, say like this. So that delta E is 0. In this case, our phase difference will depend only on delta P and X. So it will be minus P2 minus P1 X. Agree? So, when we compute phase difference, we will have two terms. One is difference of energy multiplied by T, and difference of momenta multiplied by X. So if delta E is 0, then my phase difference is just given by difference of momenta multiplied by X distance. Okay? Now, in most of the cases we have ultra-relativistic neutrinos when momentum is much bigger than the mass of neutrinos. In this case, we can write pi I equals square root of energy I minus squared minus mass I squared, which is approximately energy minus mi squared over 2 energies. I'm always forgetting to write this. Okay? Right? So, Then in this case, delta F simply equals delta M squared over 2 energies multiplied by X. So these are this P2 and P1 difference that cancels, and so what I will have difference of these terms which are proportional to the M squared. And delta M squared is just M2 squared minus M1 squared. Okay? And actually this is standard formula for the phase difference. This is what you see in the textbooks, so that the phase is given by this expression. Mass square difference over 2 energies and then X. What's interesting that you will get the same result if you take equal momenta and not different energies. So the same will be obtained if you take P1 equals P2, but then you will have difference of energies. And again, during this expansion, you will get the same formula. And at this point, there's a confusion. So some people are saying, why you are taking equal energies, why you are taking different momenta, and big number of papers are still discussing this question. So equal energy or equal momenta, what is correct? Well, numerically they coincide. At this point, there's no question. But conceptually, if you have wave packet, you have different momenta in the wave packet, and you have different energies of the wave packet. So things are more complicated in general, right? So why use this assumption? Sometimes people are arguing that this corresponds to stationary situation. When you have kind of continuous flux or continuous production of the same state, and therefore nothing changes with time. And therefore they argue that this is correct picture, which is true. But in general, you may have not a stationary situation, and you have just neutrino produced at some moment of time, and then you follow its evolution. Now let me discuss general considerations so that you will not worry much about this. So in general, you have different delta E and different delta P. Can you guess what you will get in arbitrary case? Can one guess? You will get some correction. So let me show you. Otherwise you start to write the papers on this, I'm just make your life easy, not waste time. So, in general, you have delta E and delta P not equal 0, and so you have delta phase, which is delta E time minus delta P x. Now P is square root of energy square minus m square, and therefore delta P can be generally written as delta P derivative over dE delta E. So what I want to say that actually delta E is not completely independent on delta P, and vice versa. So I can express actually delta P in terms of delta E and delta M squared. So this is what I'm writing. And then it will be plus delta P over d M squared delta M squared. So using this relation, I can write that the difference of delta P, so difference of P, delta P is actually can be expressed in terms of difference of energies and this additional difference of mass squared. Okay? Now I can insert this delta P into expression above. Noticing immediately that this is nothing but 1 over V group velocity. And so now what I'm doing, I'm inserting this delta P into this expression for delta F, and I will get the following result. Let me write it. It's a trivial thing, and nothing conceptual here. And I can compute also these derivatives, of course, explicitly using this expression. So since I know what is exactly this, I can compute dP over dE or dP over dm squared. And finally, I will get delta E, then T minus X V group plus delta m squared to Px, where P can be substituted by energy, and you see that I'm getting this standard expression, but also this additional term. You can check, it's just trivial thing, so I collected. So last one is just coming from this, and the first one is coming when I combine this and that one. Now, what is this additional term? I can write the expression in the brackets as 1 over V group T minus X. And since I have wave packet, and usually there's exponential suppression in the tails, then this should be all the size of the width of the wave packet. Do you see this? Since the wave packet, non-zero value of everything here is within the wave packet, then typical difference in my problem between X and V group T, and this is just describing the motion of my group, my wave packet, that should be of the order of sigma X. Now, delta E average, this is difference of average energy, so again I'm forgetting here to write this, is proportional to delta m squared over to have correct dimensional to energies. So of course if delta m squared is 0, then you have completely the same kinematics for U1 and U2, and therefore average energy should be the same. So that this delta E should be proportional to delta m squared. And to have right dimensions, I'm writing here 2 energies. So what I'm getting here, that this additional term is given by delta m squared over 2 energies multiplied by sigma x. So it's of the order of this quantity. So this is nothing but additional phase which is acquired over the distance sigma x. So this gives me additional phase to the standard one, which is acquired over the distance sigma x. So here you see it's x, and that is sigma x. And sigma x in most of the cases is much, much smaller than x. So for sigma x can be, for instance, 10 to the minus 8 centimeters. So if I can, yeah. And we are discussing oscillations effects over meters or hundreds of meters. There's another interesting thing. I haven't yet introduced oscillation lengths. So that can be expressed like inverse of oscillation lengths. And therefore, that describes oscillations in this sigma x small range. Sigma x is determined actually by the size of your production region or detection region with some Lorentz shrinking. So finally what you get is that this is oscillation which is acquired along the detector or along the region where your neutrinos are produced. And in most of the cases, it's negligible. If it is not negligible, that produces additional averaging effect of oscillations. So in principle, that has physical meaning, this additional term. So in most of the cases, we are neglecting this. And we are coming back to our usual expression. For the case. So now we are in a position to derive oscillation formula and the probability for oscillations. So our evolution states, evolved state, can be written as f, and what I assume here, for time being, then I will discuss possible deviation, that f1 equals f2 equals f, and therefore I can put out of this shape factor. So for time being, I'm neglecting separation of the wave packets. What I have inside is cosine mu1 plus sine plus sine mu2 multiplied by I minus delta phi. So, and what I did here, I put out the term f1, because eventually I will compute moduli square of this expression, so I can remove one of these phases. So here there is no phase. And here I have then phase difference. This is what has physical meaning. Now, this is, for instance, for electron neutrino, initially produced electron neutrino. And I'm wondering what is the amplitude of transition of mu e to mu a. Notice that electron neutrino is when this phase is 0. And then we have this cosine mu1 sine mu2. And then we have mu a, which is cosine mu2 minus sine mu1. And these two states are orthogonal. They are orthogonal. So let me put it here. Orthogonal mu e and mu a, which means that this mu e or mu a equals 0. And this is because of this orthogonality. And this happens in the moment of time t equals 0 when delta phi is 0. However, what's going on? The system propagates, develops, phase becomes non-zero, delta f, and therefore this state, which is what actually evolved out of electron neutrino, is already not orthogonal to this one, because of presence of this phase. And this is oscillation effect. So you have propagation, you have development of the phase difference, and your initially produced electron neutrino state, when it starts to develop, becomes non-orthogonal to the state mu a. And so you will have transition between mu a and this evolved state. So that although this is 0, however, mu e taken in the moment of time xt, mu a, that is already non-zero. So I should add here prime, because it's already not electron neutrino once this phase appears. Okay? So let us compute then the probability of this transition. So the amplitude of mu e go to mu a. So for this I need to compute the matrix element mu a nu xt, right? So nu xt is this just precise the state. So this is the amplitude of transition of nu a and nu e to nu a. So what I'm doing, now I'm substituting this into this matrix element, and I'm substituting here, what is this? Right? So, I also use orthogonality that nu I, nu j is delta ij, as it should be, right? So these are two different states, two different particles. And then I will not do this because this is just arithmetic. So what you do, you will use this amplitude, insert this nu a in terms of nu 2 and nu 1, insert this state as again combination of nu 1 and nu 2, use orthogonality, and you will come back to the, come eventually to this expression, f minus sc plus sc e minus I delta f. Okay. So that can be rewritten as minus f s c, and here is 1 minus exponent minus I delta phi. Agree? So this is the amplitude of transition of nu e to nu a over the distance x. Or the phase actually depends on x. Agree? Let us now compute probability, the oscillation probability. And for this we need to do the following. P nu e go to nu a equals integral, I need to integrate over time, so dt nu e, and here is nu xt moduli square. And I'm interested in actually observation of, sorry, this is nu e. This is nu e. I'm interested in observation of my nu e in my detector, and here I can put L, which is the distance between the source and the detector baseline. So that's what I'm computing. And now the things develop like this. So it's from minus infinity to plus infinity, dt s squared c squared 1 minus exponent minus I delta f moduli square, and my xt moduli square factor. So that is my shape factor moduli square. Now what is important that if delta f doesn't change substantially over the wave packet. So I integrate this expression with this shape factor, which has such a form, right? And if phase difference between these two wave packets in different places of the wave packet is the same, so I have some delta f here, I have some delta f here, I have some delta f here, and if that doesn't change substantially along the wave packet, then I can put this out. You see, it's simple, but not as simple as you can find in textbooks. But then try to catch me if I'm cheating somewhere. So then I can put this out from the integration. So if delta phi changes negligibly over the wave packet. So to say, this is the most fastly changing with time factor. This is very slowly changing with time. So I can put this slow changing factor out of the integral, and what I will get is that P equals S squared C squared 1 minus exponent minus R delta phi moduli squared, and then this integral dt, then it should be f lt moduli squared, and as we discussed, this is normalized to 1. So which means that our answer doesn't depend really in this case on the shape of the factor, just the shape disappears when you do normalization. This is not the case when we take into account different group velocities. In this case, I cannot put out f as I did before, and I need to keep f1 and f2 near this term, so attached to the two mass terms, correspond to two masses. And therefore, cross terms, when I consider interference, will depend on f1 x minus group velocity 1 t multiplied by f2 x minus group velocity 2 t. So I will have cross term when I consider this interference. Actually, this factor should be staying here and there. So that's f1 and f2, and I cannot put it out. The integration of these is non-trivial if you have separation of the wave packets. And then you need to know really the shape of the factor. Because of different group velocities, they shift, and you will have this effect precisely what I have discussed. They will shift each other. And what will contribute is just the overlap part. So in this way you will suppress interference effects. So here it will be f1, here it will be f2. I need to add this instead of writing this common expression. Okay? And so that's it. Taking into account that integral is 1, and then explicitly writing this moduli square, I will have for the probability the following expression. It will be sine square 2 theta multiplied by sine square delta m square over 4 energies and L. So this is final oscillation formula. And also what I use explicit expression for delta F. So that leads to such an oscillation formula. I can draw some picture of dependence of P on X, and it will have such a form. Right? So the depth of oscillations is given by sine square 2 theta, right? So that sine square 2 theta appears from this. Now I can introduce the lengths of oscillations. And the lengths of oscillation when the phase changes by 2 pi, right? And that gives me expression for the oscillation length, which corresponds to delta phi equal 2 pi. So the system came back to initial state when delta phi is 2 pi. And then this L nu, if I insert explicit expression for delta phi, will be given by 4 pi energy over delta m squared. And we will have some exercises to play with this formula. Numerically, one can write this as 2.5 meters energy in MeVs over delta m squared in electron volt squared. And we will have some exercises to play with this. So what is interesting that the oscillation length is inversely proportional to delta m squared. So the smaller delta m squared, small mass difference, then the longer it should be baseline to observe oscillations. This is actually why we do not see transition of, say, electron neutrino to muon neutrino to electron when we have short distances. Like in the early experiments when people establish difference between electron and muon neutrino, they have short baseline, and so just oscillations had no time to develop. So we were sitting somewhere here, and you need to have long enough distance to have oscillations. So that's it about oscillations. Let me conclude. Actually, in the previous years, I discussed also discovery of oscillations. So those oscillations have been discovered, and probably this will be my final comment. In atmospheric neutrino, the first announcement of discovery of oscillations was to study effects in atmospheric neutrinos. So the announcement was in 1998, and Taiki Kochita got a Nobel Prize for this analysis. Actually, there are interesting stories related to this stuff. What are these atmospheric neutrinos? So it's atmospheric neutrinos and superkamiokande. So atmospheric neutrinos, you have cosmic rays which produce pions, which decay into nu mu and muon, and then muon decays into nu mu electron and electron neutrino. So you have two muon neutrinos and one electron neutrino in each of these decays, and therefore you expect that the flux of muon neutrino is 2 times bigger than the flux of electron neutrino. And the first indication that something goes wrong was even in early days, say in 1988, when Toshiba-san actually recognized that something wrong is going because the observed ratio of so-called new light events produced by muon neutrino over E-light events was close to 1 and not 2. So which means that muon neutrino flux somehow disappears or something happens with muon neutrino flux. That was in early days. Final confirmation, and already people saw that maybe there is some oscillation effect. It was almost immediately in 80s already suggested. So the final was observation or measurements by super K, the angular dependence of events in superkamiokande detector. So superkamiokande detector, and they detect events coming from different directions. So neutrinos are passing the Earth and produce electrons and or muons in the detector. You see? In different directions, if you see different directions, neutrinos arrived from different directions have different lengths of propagation because they are produced in atmosphere, they are produced somewhere here. And therefore those neutrinos are propagating big distance, these propagate small distance. And therefore, using this angle of dependence, you can actually see this oscillatory picture. That has been observed, and that was discovered, considered as discovery of oscillations. So what happened happens that for neutrinos which are arriving from this direction, from up, the distance is too small. And for energies they are studying. They studied energies of neutrinos around 1 GeV. Again, you will have an exercise, you will check it. So, for neutrinos which are coming from up, distance is small and there is no oscillation effect. For neutrinos which are coming from down to up, the effect is strong and you can observe oscillation effect. And so what they have actually found is this effective probability of survival of muon neutrino as the function of L over E. So L depends on theta. So L is the distance traveled by neutrinos from the production point. And what they saw actually, what they expect to see is the following. No effect at small L. So actually this is what you can find from oscillation formula, but this is an energy scale, energy is in work. So if you use the formula for oscillations, and I have derived the formula for transition, and this is for survival, which is 1 minus P transition. So you can introduce survival probability. This is what you expect, but of course due to averaging effect, what finally has been observed is something like this. The first oscillation minimum and then the average effect. So that has been observed. And explained by oscillations, by neutrino oscillations. So another Nobel Prize, another Nobel laureate was Art MacDonald, who used different source of neutrinos from the sun. But that requires knowledge of matter effects on oscillations. So neutrino oscillations are affected by matter effect. Here it's very small, surprisingly, but there is a good reason for this. So here what we do is oscillations of nu mu to nu tau. And nu tau produce a much smaller effect, at least in this setup. So essentially you see disappearance of neutrino signal. Questions?
I have questions about about the mass eigenstate. So suppose we are experimentally observing a beta decay, neutron coming and it decaying into proton, electron and electron neutrino, and we measure the incoming momentum and energy and also the outgoing particles like proton and electron. We can measure for the neutrino directly, but we can measure the ones for proton and electron.
Yes.
And we calculate the missing momentum, which is for the momentum of the neutrino.
Yes.
And from that we measure the P nu, the mass of the neutrino.
Yes.
What will so it will be some mixture of the mass, the mass of mu1 and mu2.
Yes. So remember I mentioned this tritium decay or beta decays. And so let me just show the end point of the spectrum. So you expect for zero mass something like this. If you have masses of neutrinos, then you see like this, where that corresponds to M1, that corresponds to M2 if you have normal hierarchy, and this corresponds to M3, M2, and this is M1. If M1 is smallest. So you see this kind of structure, so something like that. And of course coherence here doesn't play at all, so in these measurements you just break coherence, and you should consider that you have the process with production of nu1, nu2, and nu3. So again, next week I'm here. You can send me mail if you want to discuss, and then we will arrange some meeting with some of you, or if we can discuss how it will work. And finally, about the exam, which I promised to say, the exam is oral. Okay, so which means that the questions during the exam are what you see in the program. And I will put the questions only those which I have discussed during the course. So because in the program you see some issues which we have not discussed here, like for instance Higgs discovery, or things like this. So only things which we have displayed here during lectures will be as a questions. For instance, one of the questions can be parity violation, or another question can be, I don't know, discovery of muon. So randomly you will select these questions. So you will select. I will arrange this, and then you will sit and prepare to answer question. Can probably make some notes, and then we will discuss. Okay? So if I see that you know the question, then fine. So sometimes I'm giving some additional questions just to see if you have some knowledge of the rest of the course. So short questions. So that's 3 components of during the exam. Usually it's half an hour per person. So what I will do, I will arrange that not everybody will be sitting. So say 2 people come to 10, so around 10 a.m. Then next to say 10:30, sorry, 11:30, then in 1.5 hours, so then we will do in this way. So one can sit down and prepare. If one wants to sit down long, it will be 2 hours. That's fine for me to prepare. And then, you know, the questions usually I'm discussing quite short. Yes, I need to have some feeling if you understand or not. And please remember one simple thing. My goal is to give fair grades, which means those who really know should have a higher grade. Those who do not know will get a lower grade. This is one thing. And the second one, should not be too much discouraged, because if someone doesn't get a high grade, it doesn't mean that you failed completely. So we had many examples where the guys who didn't accomplish well during the exam then make a much better career than those who were, you know, at high level here. So it's not the end of the story in your scientific life. Okay? So I will send some more mails. Then I expect that everybody will give me, because not everybody give me exercise number 4. Exercise number 5, you bring with you only, and I will check during the exam. Okay? And may have some questions concerning to this, the last series of homework. Okay, so then if you have questions, just send me, and we will arrange how we will discuss next week. Probably again, I will come just for just once. So, but we can spend some hours, so 2 hours, 3 hours, I don't know. Okay? That's it.